Uh, Good afternoon, everyone. I'm Wang, a postdoc from Dr. Shi's lab. Today's presentation will focus on exploring the approaches to clinical concept normalization, and I'm really glad to discuss this with you all here. So, for the entire during the presentation, I'll start with an introduction to the background and importance of clinical concept normalization. And next, I will review some related works about this task. Following that, I'll divide to our methodology, explaining the approach we use to address the challenges in this area. Then I'll share the results from our experiments and demonstrating the effectiveness of our approach. Finally, I will wrap up with the conclusion, summarizing our contributions and discussing limitations and future works. So for the first part, the concept normalization is really crucial in NLP tasks, especially in information extraction. It involves linking identified entities in a text to standardized concepts in a knowledge base, dictionary, or ontology. This process is also known by other terms like normalization, concept mapping, and so from the definition, concept normalization involves two key steps, the entity identification and entity normalization. So as shown in this figure, we can find the entity identification is extracting main entities with specific types from texts, such as disease, medication, procedure, and so on. After that, these entities will be normalized using different medical knowledge bases like SNOMED-CT, ICD-10, and UMLS, and to get the relevant concept IDs. So next, I will provide an example to demonstrate how concept normalization is achieved in the clinical domain. So, for example, there are three entities in this sentence I've shown here. After the first step, the entity normalization, we will get the basic entity types for these entities. We will get the diabetes with the disease type, or the insulin with the medication type. After that, we will use certain normalization algorithms to mapping these entities to standardized concepts. For example, we can make the diabetes to concept type 2 diabetes mellitus. Finally, retrieve these normalized concepts from medical knowledge base to obtain the corresponding concept ID. For example, we can get the concept ID D11 for the entity diabetes from the ICD-10 CF knowledge base. We can also get the UMLS-LLaMA for the diabetes from the UMLS ID for the diabetes from the UMLS database. In general, the major challenges for the clinical concept normalization are ambiguity, variation, and absence. The ambiguity occurs when a single term or phrase can refer to multiple different concepts. For example, when a code appears in the text, it probably means a kind of condition, a common code, or observation code cessation, or a procedure code therapy. Variation refers to the same concept is represented by different entity mentions. For example, the terms like diabetes, PM, sugar disease, and diabetes mellitus type 2 are all represented by the same condition concepts that we analyze. Additionally, the data absence occurs when novel entity dimensions cannot be linked to any concept in the available knowledge base. So I'm absolutely sure that before 2020, no one had any idea what COVID-19 was. So among these challenges, the variation is far more prevalent than ambiguity and absence in clinical application. For example, if we want to identify the patients with chronic kidney disease in free text medical records, it will be challenging due to the different terms used to describe this condition, like CKD or chronic renal failure, and so on. So only relying on keyword searches may result in inconsistency and inefficiency. However, if we use the standardized identifier like the UMLS code, can simplify this process, ensuring more reliable and consistent detection of CKD across patient records. So develop high-performance concept normalization algorithms to mitigate the negative impact of the variation issue is of great interest to the clinical field. It's not only enhancing the accuracy of patient identification, but also supporting the better clinical decision-making and improving overall patient management. Next, I will introduce some related works, existing works, and explore how they address these challenges through their methods. The clinical concept normalization involves mapping an entity dimension to a known standard identifier in the knowledge base. There are many existing works in this field. Generally, the methods of concept normalization are divided into traditional model, language model, and large language model. Next, I will further introduce a more fine-grained classification of these models. The first one I need to introduce the rule-based model, rule-based methods, and the machine learning-based method in the traditional model. For the rule-based methods, they mainly focus on designing rules and templates to match the relevant entities and normalize them. For example, they usually, for this paper, the authors computed identity distance patterns between all synonyms of the disorder concepts in UMLS, as well as between their mentions in the training data and the corresponding tagged concepts in the UMLS, and to normalize the entity mentions. For the machine learning method, they mainly focus on designing features for SVM series model to do classification of ranking tasks. For example, for this paper, the authors first employ the BM25 to retrieve several candidates. Then they calculate BM25 ranking score, Jack-Carr similarity score, and the translation-based ranking score as matching features, and to let the linear rank SVM to assign a final ranking score and rank these candidates. The deep learning method can automatically extract semantic features from input texts, eliminating the complexity of manual feature design and significantly enhancing the performance of concept normalization. So for this paper, the authors just use the CNN architecture to compute the similarity between entity dimensions and its relevant candidate elements. This framework is composed of 6 layers. which can be divided into two parts, semantic representation and ranking-based similarity. So for the input interdimension M, there are n candidate elements represented as E, and forming them as mentioned candidate pairs. In the training data, the data set is reconstructed based on whether the mentioned candidate pair appears in the training set. With the development of the transformer architecture, many NLP tasks have seen significant improvement due to the Bird series models. These models provide enriched semantic information after being trained on a large corpora. Generally, Bird series models not only generate embeddings, but also compute backend features for downstream tasks. So, firstly, I will introduce an embedding-based method of concept normalization task. Just for this paper shown here, the authors first gave the interdimension heart attack as an input to the transformer network. Here is a separate model, and to generate a vector representation. Then they use the NT softmax layer to compute the cosine similarity score SI. Between the interdimension and the wide weight vector for each concept in oncology. In order to model the QELAS label, they adopt a learnable scalar parameter S0 as a threshold to filter whether this entity is QELAS mentioned. Another application of a language model in the concept normalization is ranking candidate retrieved from existing algorithms such as BM25. Just like this paper shows here, the entire framework has 4 modules. For giving an entity dimension M and knowledge base which consists of a set of UMLS concepts. This system pre-precise the input entity M at each concept in the knowledge base with the following strategies like spelling correction, abbreviation, resolution, and so on. For the candidate concept generation, they generated the candidate concepts for each mention with 2 steps. The first step is they index all the concept names with the training data, with the training mentions with their concept IDs. Then they imply the traditional LLM model of BM25 to retrieve the top 10 candidate concepts. For the candidate concept ranking module, they ranked the candidate concepts by fine-tuning the pre-trained bird, bear-bird, or clinical bird models, where they transform the ranking task as a census pair classification task. In the end, if there were no candidate concepts returned from the BM25, they predict M as an unlinkable motion. The emergence of large language models marks a significant turning point in the field of NLP. The prompt engineering has become a crucial technique in this field. The prompt engineering involves designing and optimizing input prompts to get the language model in producing specific outputs. Many researchers consider using prompt engineering of LLMs to mitigate the challenges in these tasks. Just like this paper shown here, the authors firstly prompt LLM to generate alternative phrasing or synonyms of a given input text span to be normalized. Then they use existing normalization system like quick UMLS and BM25 to attempt to normalize normalize both the source text span as well as candidate alternative span. After normalization, they again use a prompt LLM to filter out inappropriate concepts using both the preferred name and the semantic type of the given candidate concept, as well as surrounding context of the original identified span. In addition to prompt engineering, instruction tuning for LLMs is also a significant approach to enhancing performance in this task. For this paper, the authors wanted to fine-tune LLM using a vocabulary-derived corpus to overcome these challenges. The basic model is LLaMA 2 7 billion model. They fine-tune the model on a newly organized dataset derived from the HPO vocabulary. They fine-tuned the two LLaMA 2 HPO normalization models. The initial model was fine-tuned using only standard HPO concept names without providing any synonyms. The second one was fine-tuned using standard concept names with half of each concept's associated synonyms. The model will not be finished training until the accuracy on training data more than 99%.
What did they do to improve the performance if it's not 99%?
Because the data set just constructed by themselves, they just use to decide they decide different prompt tablets to training the LLaMA 2 model, and after finish the training, they use the following 3 tasks to test whether the performance will be improved. For example, they can evaluate model with just use prompt engineering prompts to see whether the normalization performance improved, or also use some just like the training process, use a sim test process to test the data set to evaluate the performance. And in the end, they also compare with the existing large language models such as GPT model to see.
So what did they do? If it's not 99%, they manually change the prompt? They try different prompt?
No, they didn't to show this in depth in their papers. They just they will continue to training these models. If the performance, if the accuracy not reached to the 99%, then maybe change another way to training this model. But they didn't show the details about this. For the concept normalization task, the concept normalization task is a complex and knowledge intensive task. So it's probably to build a language model based on system that access external knowledge source to this task, namely RAG framework. The first stage of this framework transform textual data into semantic representations using different embedded models such as Cybird, PyMapBird, GPT-3, and LLaMA model. This process generates high quality embeddings for both the concept name string and combined version that includes the name string along with its context. Following the generation of textual embeddings, they process all embeddings from the ontology into a vector database and prefer to as a long-term memory store. The top key candidates will be retrieved based on the causing similarity between embeddings of the query entity and all ontology. Finally, a prompt is constructed that combines the query with candidates for ranking using different large language models like GPT-3, GPT-4, and Llama model, resulting in reasonable outcomes. Well, the two-stage retrieval method based on embeddings have demonstrated strong mapping performance, but it still presents two limitations that needs further improved. Firstly, there is a lack of embedders specifically for medical terminology. Although traditional embedders such as BERT, clinical BERT, and GPT embedder offer rich semantic representation, they cannot accurately capture the semantics of medical terms. Furthermore, the current two-stage retrieval framework needs development of distinct embedders and redirectors for different tasks, which is independent of the retrieval and RAG stage and will bring deviations for this two-stage framework. So next, I will introduce our framework to and demonstrating how we need to mitigate the challenges in these tasks. So as this figure shown here, our entire framework also can be divided into two stages: the retrieval stage and the RAG stage. For a given input query containing an entity and its surrounding context, we will input this query into the pro-processing modules to process the query entity. For example, for the entity DDI, after pro-processing, we will get the lowercase DDI, and also we can get several expanding full names of the abbreviation DDI. After that, the pro-processed the entity was then combined with the entity embedding generated from our UMLS-LLaMA to retrieve the relevant candidate concepts from the indexing library via the hybrid approach. The indexing library consists of the text index and the embedding index. The text index is used to identify most exact match concept based on the lexical similarity, while the embedding index is implied to find the most semantically similar concept based on the representation similarity. After combining the retrieval, after obtaining several relevant candidates, we combine the query with these candidate concepts to create a prompt, and we input this prompt into our UMLS-LLaMA again to generate a new ranking for the candidates and identify the most relevant concept for the query entity. So next, I will introduce how to train our UMLS-LLaMA for both retrieval and RAG stage, and how to build the indexing library at the retrieval stage. In order to train the UMLS-LLaMA at embedder and the retrieval stage, the first thing is to construct a synonym database. In this study, the primary focus is on developing an embedder based on UMLS data. Specifically, we use the UMLS 2023 AB version to filter concepts corresponding to 4 common semantic types, such as disease diagnosis, procedure, drug, and measurement, and then to construct an instruction tuning synonym data set to training UMLS-LLaMA as an embedder. More specifically, for the filtered UMLS 2023 AB data, we process this data by the following 3 steps. First one, the selected items is in English, and second one, the selected item is not discarded. The third one is the select item contains at least one word or number. After processing, we start to extract positive samples as a synonym and the negative samples as the non-synonyms. For the positive sample selection, just giving 2 terms, X and Y, that are categorized under the same UMLS ID. If X and Y originate from different source vocabularies, we will constitute a positive sample X and Y. In other words, we will think the terms X and Y are synonyms. For example, just consider the hypertension from the normalization vocabulary and high blood pressure from the MASH vocabulary. These 2 terms would form a positive sample. For the negative sample selection, just like the strategy of generating positive sample, for a positive sample X and Y, we will replace Y with X most semantic similar atom key to form a negative sample X key. More specifically, P is not from X source vocabulary and not equal to any of X synonyms. The semantic similarity between 2 atoms is calculated by constant similarity based on the clinical bird embedding. In certain cases, there might be multiple positive samples that include the concept X. In these instances, we will select the next high semantic similarity similar atoms to create the second negative samples. After extracting synonyms and non-synonyms for each concept in the UMLS, we finally use these prompt templates to further construct an instruction tuning synonym dataset. After
What's
constructing
the ratio between positive and negative samples? How many negative samples?
Almost 1 vs 1. Around 100 million positive sample and 100 million negative samples.
My question will not be a negative sample.
Oh, sorry.
Those 2 pair.
But are you taking for the concept name 1 and concept name 2, 1 from a positive sample and 1 from a negative sample?
No, I haven't considered that. I just consider the name if they are from the same concept ID, but not from the different source vocabulary. I just regard them as a positive. For the negative, I just use one of the concept name in the positive one to retrieve the negative several negative samples, several negative concept. The negative concept is actually a different concept ID, and it actually is different source of vocabulary. So after constructing the synonyms dataset, we will train the LLaMA 38 billion instructor model to obtain the UMLS-LLaMA model, and combine with the LLM back-to-back framework to transform the UMLS-LLaMA to an embedder. After getting this embedder, we can create the index library to generate concept candidates during retrieval. For our index library, we use the UMLS data, membership data, and task-specific training data to design 3 categories of index library by different combinations. Specifically, for each entity mentions with annotated GUI in the dimension and the task-specific training data, we removed. Firstly, we removed all entity mentions with a GUI-less label. We can call it as GUI-less cleaning. Next, we use the annotated GUI to search for specific concept information, such as preferred name, AUI, SAB, and other relevant details via the UMLS API. And that to construct the text index. It is noted that the UMLS 2023 AB itself serves as the text index. So we only convert the mention and task-specific training data to the UMLS format. Finally, we feed all the terms into our embedder to generate the embedding and construct the embedding index. Similar to training UMLS-LLaMA at the retrieval stage, the key to training UMLS-LLaMA at the redirect stage is first constructing an appropriate ranking data set. Here, we only use the task-specific training data to construct the relevant data set. Specifically, for the task-specific training data, we first use the method of our retrieval stage to generate several initial concept candidates. Then we do the following steps to process these initial candidates. The first one is if none of these candidates included the correct answer, we randomly replace one of these candidates with a corresponding annotated concept from the training data. The number 2 is we added a GUI-less label to the pool of the candidates. Finally, this process allowed us to create a candidate pool for each private entity in the training data. After that, we will follow these 2 templates to construct this instruction tuning ranking data set.
Can you go back? I don't quite get it. What did you do?
Specifically, just I will need the first stage, the retrieval stage method to training to retrieve some initial candidates from the task-specific training data, and for the if we get some candidates, I will do the 2 steps to optimize these candidates. The first one, maybe in some cases, the retrieval results don't contain any correct answer, but we have the annotated answer, annotated label. So I just randomly replace one of the wrong or incorrect answer with the correct answer. The second one is because
I mean replace a candidate with true label.
True label means the annotated in the training set, the annotated GUI in the training set. Because after retrieving, we don't always get the if we get the 10 candidates, most of the situations it don't include any correct answer. So if I want to build the ranking data set, it must have a correct answer in this candidates pools. So I need to according to the training data set to find the correct answer and input and replace the incorrect answer with the correct answer.
So your retrieval is based on a logic.
Oh yeah, because the first stage I have trained the I have got the UMLS embedder and use the hybrid retrieval method to get several candidates. So it uses a large language model. But for the large language model, just to focus on generating embeddings, not to generate any correct answers.
So you mean to say that the retrieval stage will not have the correct answer always?
Yes.
And that's why you're taking the original annotated set and replacing one of the wrong ones with the true ones.
Yes. After I replace get the true candidates, I can construct the ranking data set because the ranking data set must have the at least one true correct at least one correct answer and several incorrect answer.
And for each training sample, you also add a query-less label as such to it.
Yes. Following the same hyperparameter settings and devices used for instruction fine-tuning and the retrieval stage, we further treat our UMLS-LLaMA model on a ranking data set. For the task-specific data sets, there are three notable shared tasks focused on biomedical concept normalization in clinical nodes. SAM-EVA 2014, SAM-EVA 2015, and N2C2 2019. For the first two tasks, primarily address the normalization of disease motions using the shared corpus. On the other hand, the N2C2 data set implies the biomedical concept normalization corpus and extends the scope to include a wider area of concepts such as medical problems, treatments, and tests. Additionally, the annotated quizzes in the SAM-EVA 2014 and 2015 are derived from the normalizity subset of the UMLS 2012 AB version. While the N2C2 dataset use the quizzes from the normalizity and ArcNorm subsets of the UMLS 2017 AB version. In contrast, we use the UMLS 2023 version to construct our database. As a result, about 0.88% of quizzes in the SAM-EVA 2014 dataset, 1.29% in the SAM-EVA 2015 dataset, and 0.25% in the N2C dataset have been modified or removed. So we corrected these quizzes using the UMLS API before training and testing our framework. For all experiments, we utilize the standard evaluation metrics of top K accuracy for clinical concept normalization, measuring the percentage of entity motions that were correctly normalized. Specifically, we defined accuracy and 1, accuracy and 5, accuracy and 10 to assess our framework's performance. So next, I will share some results of our framework. And the first result is for the retrieval stage. We use the clinical bird as well as large language models like GPT and LLaMA to construct embedders for retrieving relevant concepts based on semantic similarity. In contrast, BM25 implies an exam match approach for concept retrieval. So these three figures represent the retrieval results from the UMLS-only indexing library on 3 data sets. The blue bar means the accuracy at 1, the green bar means accuracy at 5, and the red bar means accuracy at 10. From these figures, we can find if we use the clinical bird as an embedder, we will get the worst performance among these methods, even worse than that of BM25. For the GPT embedder and the Llama 3 model, despite neither being treated with the specific terminology knowledge, their performance differs significantly. The GPT embedder consistently outperforms the Llama 3 model, particularly on the SEMIVA 2015 and N2C2 dataset, where the GPT embedder achieves around 6 higher accuracy. For our fine-tuned UMLS-LLaMA model, because of training with the terminology data, it can generate the effective embeddings for query entity mention and achieve the best retrieval performance across all data sets. After combining the UMLS with the mention dataset to build a new indexing library, the performance of all methods improved slightly compared to the UMLS only indexing library. However, the ranking of the different methods' performance remained unchanged. The BM25 achieved above average performance. Clinical bird still obtained the worst retrieval performance among all methods. The performance of GPT embedder is close to that of fine-tuned UMLS-LLaMA model. If we combine the task-specific training data with the previous index library, we will be surprised to find that the retrieval performance of all methods improves significantly, even though the ranking of the different methods' performance remains unchanged. However, the accuracy at one of the clinical bird model is very close to the BM25 across all these three data sets. Additionally, there is no significant gap among the accuracy at 1, accuracy at 5, and accuracy at 10 for the clinical model. For the large language models, although the accuracy at 1 does not achieve satisfactory results, the accuracy at 5 and even accuracy at 10 suggests that applying an effective ranking algorithm could yield the best performance by reordering these results. It is worth noting that our UMLS-LLaMA hybrid retrieval method consistently achieves the best performance regardless of the type of the indexing library used. Next, I will explore the performance of our UMLS-LLaMA model on the ranking task. At the redirect stage, we use the best results from the retrieval stage obtained through our UMLS-LLaMA hybrid method. We then applied baseline records to order the candidate concepts and compared their performance against our UMLS-LLaMA record. Here, we used 3 different records as baseline models to compare with our method. This table presents the performance of different record models on these 3 data sets and measured by accuracy and 1. Among these models, the UMLS-LLaMA consistently outperforms the others, achieving the highest accuracy and 1 score across all data sets. The GPT-4o model follows closely, particularly on the SEMIVA dataset, with accuracy and 1 scores of 91% and 90% respectively. The bird large model also shows strong performance, especially on SEMIVA 2014 with 90%, though it lags slightly behind on the other dataset. The Llama 3 model, while still competitive, ranks lowest among these models. Overall, our UMLS-LLaMA model demonstrates superior ranking capabilities across all tested datasets. In addition, we compared the best concept normalization results from our framework with the following sort-out methods. Compared to the other sort-out methods, our framework achieves the best performance on some EVA 2014 and 2015 dataset, but the second performance on N2C2 dataset. After our investigation, we found two reasons. Firstly, there is a relatively high lexical overlap between the interdimensions in the training and test sets for the SAMIVA datasets. For example, in the SAMIVA 2014 dataset, about 30% of the interdimensions in the test set also appearing in the training site. In contrast, the N2C2 dataset has less than 5% overlap. Additionally, due to the lower lexical overlap in N2C2, capturing semantics becomes more crucial. Our UMLS-LLaMA embedder is trained on UMLS terminology rather than task-specific training data. However, the KN-based method fine-tunes the separate embedder based on the N2C2 training site, which is why they achieve the best performance on the N2C2 dataset.
So you also trained on that N2C2 dataset, right?
Yeah.
You have task specific.
You mean me?
Yeah, the
yeah.
85.39. Is that also?
Oh no, I
trained-
just
Or this is without using N2C2?
yeah, without using N2C2. Just actually, I just use the N2C2 to training the N2C2 dataset with as a record stage, as a re-rank stage. I just use this dataset to training the re-ranker, not training the embedder. So for the embedder size, it may be it may not get the correct answers or correct candidates. If we also further use the re-ranker, it also cannot get the correct answer. For the embedder, I didn't use the task specific data to training it. I just trained the re-ranker use the task specific data. So
what about those methods?
For the KN-based method, they just use the embedder to generate the embedding, generate the candidates. Don't use any re-ranker method to re-rank these candidates.
So they even didn't use re-ranker?
For the KNN model, yeah, they didn't use a re-ranker. Just use a spammer model to generate the candidates. They also they only report the accuracy and Wang performance. So I think this maybe is a key point that why they have achieve the best performance, because they use the training data to also fine tuning or training the embedder of some other models.
I don't know, the training data is so small, only 50.
Oh no.
They train the.
Actually, they are not just use the training data. Firstly they use the Snowman City database to generate embedding, and also use the training data to fine tuning separate and also in order to generating the task specific the embeddings for the N2C2 dataset. So they use two embeddings. The first one just use the Snowman City embedding, but they didn't training this data. But for the N2C2, they use this training data to fine tune this separate model and generating the embeddings for the test data set. In the end, I will summarize our whole works. The first, I will summarize the contribution of our framework. The first contribution is we proposed the UMLS-LLaMA as a UMLS embedder focused on generating medical terminology embeddings using LLM. This embedder implies instruction tuning to improve the representation capability of medical term. Based on the UMLS-LLaMA model, we further employed task-specific training data to instruction tuning it, creating a LLM-based re-ranker. This re-ranker can quickly and effectively re-rank candidate concepts obtained from the retrieval stage. Finally, we constructed a concept normalization framework based on the drag method using the unified UMLS-LLaMA model. This framework was evaluated on 3 clinical relevance data sets and achieved competitive performance. However, our work also has some limitations. The first limitation is we haven't considered using the graph structure in the UMLS to train our model. Because in UMLS there are several graph structured relationships that have defined how different medical concepts are related to each other, like hierarchical relationships, associated relationships, synonym relationships, and qualifier relationships. Apart from synonym relationships, we have now used the other relationships to construct a richer graph structure to assist in training a more comprehensive UMLS-LLaMA. Additionally, neither the UMLS-only indexing library nor the UMLS combined with the MedMention indexing library achieve the satisfactory performance at the retrieval stage. It means that our framework is now well suited for the handling zero-shot scenarios effectively. So in the future, I plan to design more training tasks based on the UMLS relationship tables, definition tables, and semantic type tables to better train the UMLS-LLaMA model. As another approach to achieve richer semantic representations, we could construct a contrastive learning datasets from the tasks mentioned above, and use contrastive learning instead of instruction tuning to treat our embedder. In order to enhance traditional RAG methods for effectively handling zero-shot scenarios, we plan to develop a graph-based RAG framework. This framework will help to identify previously unseen concepts by using not only textual content, but also the relationships and the context provided by the graph. That's all for my presentations, and thanks for listening. If you have any questions, feel free to ask me. Thank you. Yes.
So when you're working with large language models, I would imagine an issue comes up is if you're also working with like UMLS IDs, the tokenization is going to be like pretty useless when you're trying to tokenize a concept ID. Is this something that anyone has looked at?
Oh, you mean the tokenization? Because for the UMLS database, it is a word or the phrase levels database, not the sentence level database. So for the tokenization part, I think it's totally no problem to tokenize this database and don't consider whether it will proceed the max length of the tokenization.
No, what I mean is if you try to tokenize like UL20036.
Oh, I don't have to tokenize the concept ID, just to tokenize the words or phrase. After the tokenize the word or phrase, input it to the large language model and generate embedding, I will use the generated embedding and the corresponding UMLS ID or concept ID and combine them as pairs to store in the stored it in the database. So I don't have to tokenize UMLS ID to do that.
What is, when you say zero-shot performance is not, what do you mean?
I mean, cause I have
Conclusion, okay. Next, yeah.
because I designed three different indexing library. The first one just a UMLS only indexing library. The second one is UMLS only plus MetaMention dataset. The third one is UMLS plus MetaMention plus task specific training data. So for the tasks, for the third index library, I added the task. I added the training data in the library. So so for this situation, I think it's not the
Do you have the result for this zero-shot scenario? Your previous table, do you have a result showing the zero-shot scenario, which is basically just using the
actually,
LLaMA index, right? The UMLS.
yeah, because I just regarded that
Do you have the numbers for that zero-shot scenario?
I have to test the actually zero shot scenario.
Then how can you say it's not good? I mean,
Because I mean I didn't use any training data for this task.
yeah, that's why. Do you have a number to show it's not good? I just want to see how bad it is. So this is plus, yeah, is this the result?
Yes.
Is it zero shot? You say UMLS only, you mean the zero shot is UMLS only?
Yeah, because in the UMLS only,
Then is this not good?
it's not good. It just around 50 or 60%.
Which one? Can you point to me?
So yeah,
Accuracy at 1,
yeah, accuracy at one is really
54 compared to GPT.
GPT. 54 just for the Llama 3 model. Our fine-tuned model is 60%, around 60%, and the GPT is
Yeah, that's my question. Why you say it's not good? It's better than GPT.
I just for the entire framework, I think maybe it will reach to 70%. Maybe it's good performance. I just think. Because
When you say good or bad, it's always compared to something. You have a baseline.
okay, because I just if we add the task-specific training data, the performance will improve a lot compared with without the training data. So for this situation, I think the zero shot performance may be not good.
Okay, I see what you mean. Other questions? Okay, thanks again.